Hello, we're Group 15. The subject of our capstone project is energy generation from rainfall using triboelectric nanogenerators. With climate change becoming an increasing concern in recent years, there has been more and more focus on sources of energy that do not involve burning fossil fuels and releasing greenhouse gases. One of the major challenges in the global shift to renewable energy is the fact that renewable energy sources are not one size fits all. Different technologies are applicable to different environments and times. Here, consider a few of the most common renewable energy sources. Solar panels have the advantage of low installation cost as compared to other sources, but require either flat surfaces like rooftops or open areas. They also have the obvious requirement of sunlight, which limits optimal electricity generation to sunny days and limits the use of solar panels to locations that receive sunlight. Wind turbines and hydroelectric dams are two other common sources, but both have much higher installation costs and each have their own requirements that limit their use. Wind turbines need large open areas and a windy environment, and hydroelectricity requires a body of water. Prevalent renewable energy sources such as hydroelectric and wind power are typically large-scale power solutions, with expensive installation costs and generating large amounts of energy for the electrical grid. These are excellent technologies, but these sources are not ideal for low-cost, small-scale power generation. Solar panels have a lower installation cost and can power individual homes or devices, but have the obvious drawback of requiring sunlight, so there is a market for small-scale energy tech that can generate power without sunlight. As well, a power source that can be integrated onto existing surfaces with minimal disruption could open up new applications for renewable energy where other sources cannot be used. An attractive untapped energy source is the energy present in rain. For one, rainy weather tends to make solar panels much less effective. If we could generate power from rain, it could help to compensate for the decrease in production from solar power. As well, the prevalence of rain means that it can be used to generate power over wide areas. There are multiple sources of energy present in rain. Obviously, it carries kinetic energy, but it has also been found that falling raindrops can carry either positive or negative charges, depending on atmospheric conditions. Taking advantage of the triboelectric effect, we can use the electric charge in raindrops to generate power. First, we need to discuss triboelectricity. It's a particularly interesting phenomenon because while the exact mechanism is not currently understood, it's been demonstrated that its effects can be used to enable energy production. The triboelectric effect is a mechanism by which charges are generated when friction occurs between two materials. This phenomenon is commonly known as static electricity. When two different materials are rubbed together, a transfer of charge occurs from one material to the other, leaving a negative charge on one and a positive charge on the other. In fact, the materials do not need to be solids. Friction between solids, liquids, and even gases can lead to charge transfer. In our case, we will be taking advantage of how the triboelectric effect can produce charges in raindrops as they fall through the air. To take advantage of the triboelectric effect creating charges in rain and use it to generate power, the device that we will create is called a triboelectric nanogenerator, or TENG. But there's more to power generation than just the triboelectric effect. To create a TENG that can generate electrical power with charged raindrops, we also need to take advantage of electrostatic induction. Consider the case of, for example, a rain droplet that is carrying a positive charge. It could have obtained this charge via the triboelectric effect through friction with the air as it fell, or with another material, such as a polymer surface. If a conducting material is present near the raindrop, a negative charge will be electrostatically induced in the conductor, which means that electrons will flow through the conductor towards the positive droplet to balance out the charge. This flow of charge through the conductor can be harnessed to generate electricity. If the droplet were instead carrying a negative charge, the opposite would happen. Electrostatic induction would repel electrons within the device, and we could then harness the flow of electrons away from the droplet to generate electricity. Using these principles, we will be able to design and build a triboelectric nanogenerator that can use the electrostatic charge of raindrops to generate power. Of course, this isn't the full story of how TENGs can be used to generate electricity. The top surface of the device will need to be a thin insulating layer, with conducting electrodes spaced out beneath the insulator. This insulating layer keeps the charge on the raindrop separated from the electrodes, so the charge on the raindrop doesn't get neutralized. As we've discussed, when a positively charged raindrop first lands on the device, electrons flow to the electrode that the raindrop is over top of. As the raindrop flows down the device surface, though, it will go through alternating cycles of exiting the surface above one electrode and moving on top of the next electrode. The electrons within the device will thus leave one electrode and flow to the next. As the electrons leave each electrode, a current will be generated, but in the opposite direction from the one that was generated when the raindrop arrived. This process will repeat each time the water droplet leaves one electrode and goes to the next, with the current flowing back and forth each time. Therefore, the TENG device will generate an alternating current. To power a device or charge a storage device, we need to convert this alternating current to direct current. We can also take advantage of the triboelectric effect again here. If we carefully choose the insulator material, the friction between the water droplet and the insulator layer's surface can lead to the charge on the raindrop being increased, thereby increasing the induced current. To determine the necessary characteristics of a TENG that can extract the energy from rainfall, we first need to determine the places that we plan to implement it. An obvious benefit of a TENG that obtains energy from rain is that it can generate power when solar panels cannot. Therefore, a natural place to integrate TENG devices is on top of solar panels. When it's raining and there's no sun, power can still be generated from rain to supplement the loss of solar power. Obviously, a TENG device going on top of the solar panel would need to be transparent. A transparent TENG device could be integrated onto other surfaces as well. For example, roofs and windows receive plenty of rain, and a transparent device lends itself well to integration onto windows. Since we'll be extracting energy from rain using electrostatic charge, rather than the kinetic energy of impact itself, we can place these devices on vertical surfaces that do not receive direct impact from rain. This opens up the sides of buildings as a possible area of implementation, massively increasing the available surface area. Other places that these devices could be used include car windshields, public transportation, or billboards. To succeed in the identified areas of implementation, it's clear that our TENG device needs to have a specific set of properties. The device needs to be transparent, so that it can be integrated onto solar panels and windows. It also should be inexpensive, so that many TENGs can be used to cover wide areas. This means that not only should the materials be inexpensive themselves, but the fabrication cost of the device should be low as well. The devices need to be durable, since they must be able to withstand environmental conditions. This includes resistance to changing temperatures, precipitation, and debris. The devices should also be as efficient as possible, converting the maximum amount of energy from the rain to useful electricity. The devices should be lightweight and thin, minimizing their disruption to the function of the surfaces upon which they are integrated. And finally, since these devices will be outdoors, they should be environmentally friendly and not expose the environment to toxic materials. The main components of a TENG device are illustrated here. The bottom layer is a substrate, upon which the device will be fabricated. On top of this are the spaced electrodes. Finally, an insulating layer must be deposited on top of the electrodes to stop the raindrops from directly touching the electrodes. Of course, for the applications that we're targeting, all of these need to be transparent. Additional circuitry will also be needed, with connection to the electrodes to take the current from the device and use it elsewhere for power. There will be many considerations when designing the various components of our device.
There are a number of challenges and trade-offs which we considered while evaluating this project idea and will continue to keep in mind as we move forward. One challenge is the efficiency of the devices, as ideally the power output for the TENG devices should be maximized for use in impactful applications. Additionally, it will be challenging to integrate all of the various components of the device together, as all of them are needed for the device to operate successfully. There are also trade-offs that we'll need to consider in our design. For example, there is an inherent trade-off between device size and power output. A larger device can generate more power, but is more expensive and could limit its ease of integration. There's also a trade-off between how much we plan to innovate on different aspects of our device and how easy it is to fabricate. For example, for a device's electrodes, existing transparent electrode designs leave room for improvement in terms of their conductivity, but these improvements may require more complex fabrication steps. Our nanotechnology background will allow us to improve upon previous demonstrations of TENG technology in two main areas. First, we hope to fabricate nanostructures in our dielectric layer to improve the hydrophobicity of the TENG device's surface. As previously mentioned, we also aim to utilize transparent electrodes to expand the range of applications for a device. Indium-doped tin oxide is a frequently used transparent electrode material, but presents drawbacks due to its higher sheet resistance compared to metal electrodes, limiting device efficiency. We therefore aim to fabricate electrodes that improve device conductivity while maintaining transparency.
In terms of improvements afforded by hydrophobicity, we can reduce water adhesion to the device and thereby improve water flow across the surface of the TENG. By encouraging water to slide off quicker, we can increase the power output of the device. Furthermore, a hydrophobic surface can act as a self-cleaning mechanism, as droplets can remove particulate during the process of rolling off the device. In contrast, a flat surface without artificial roughness would simply cause the water to redistribute such particles. To further expand on the realization of hydrophobicity in our device, artificial microstructures can be fabricated in our dielectric layer to increase surface roughness and thereby increase the contact angle between water and the dielectric layer. As you can observe in the diagram, increasing the contact angle prevents liquid from spreading onto the surface, thus improving hydrophobicity compared to a conventional hydrophobic surface. Air is present in the gaps between the pillars of the microstructure, which acts as a physical barrier to liquid water. In order to fabricate these microstructures on the surface of our dielectric, we'll be employing a soft lithography technique which has been extensively researched to form structures on materials such as PDMS. It has been previously demonstrated that one can fabricate square micropillar structures in silicon, which acts as a master mold for the PDMS dielectric. Square pillars with side lengths of 2 microns by 2 microns and a total spacing between pillars of 2 microns with a depth of the pillars of 2.5 microns has been shown to develop improved hydrophobicity on PDMS. So starting with a silicon substrate, we can deposit a 2 micron layer of silicon dioxide and pattern it using conventional lithography. Maskless exposure can be carried out using the MLA maskless aligner in the quantum nanofabrication facility. Next, reactive ion etching is performed to transfer the pattern to the silicon dioxide layer. We can then perform a 2.5 micron DRAE etch of the silicon using the Bosch process to develop the microstructure pattern. In this process, the patterned silicon dioxide layer acts as the etching mask. Next, PDMS is poured into the silicon mold and cured. Once the PDMS is taken out of the mold, we obtain a pattern structure to improve surface hydrophobicity. Recently, in discussion with Dr. William Wong, it was suggested that zinc oxide nanowires could be used to create a superhydrophobic PDMS surface. This process was successfully carried out in yet to be published work, and could be an alternative route for the realization of our hydrophobic PDMS surface. Zinc oxide nanowires are grown from seeds in a random pattern on top of the PDMS dielectric layer, which generates a rough micropattern surface. Since the grown zinc oxide nanowires are hydrophilic, a conformal coating of PDMS is applied to increase the surface energy and achieve our superhydrophobic surface. Thus, we can increase the hydrophobicity of PDMS without conventional lithography and microfabrication steps, all while maintaining transparency. Again, this was a recently proposed alternative, which will be considered as a backup to our original fabrication plan. The second component we aim to improve upon is the electrodes of the TENG devices. Commonly, indium-doped tin oxide, or ITO, is used as a transparent electrode material for applications like touchscreens or solar cells. However, ITO has a lower conductivity compared to metals, reducing device efficiency. Therefore, our objective is to implement a transparent metal electrode on ITO, improving the conductivity and therefore performance of the device. Fabricating thin metal grids has been previously shown to decrease the electrode sheet resistance compared to pure ITO. With a small enough pitch and line width, the metal grid structure allows one to maintain electrode transparency with only a small decrease in transmittance. From the graph on the left, we can see that compared to a pure ITO substrate, a gold grid fabricated on top of ITO offers a much lower sheet resistance, as the gold grid provides additional high conductivity pathways for charge transport. We'll now examine the fabrication process that will be performed to fabricate gold metal grids on ITO, which will be used to realize our transparent electrodes. We start with an ITO-coated PET sheet with an ITO coating thickness of 1300 angstroms. These sheets will be procured from Sigma Aldrich. Next, we can coat the ITO/PET sheet with HDMS to improve adhesive capability and laminate the sheet on fused silica glass substrate. We then coat the structure in photoresist and pattern using conventional photolithography techniques. Maskless exposure can be again carried out using the MLA maskless aligner. The line widths for the grid will be 10 microns, while the grid pitch will be 80 microns. Next, A thin 5 nanometer layer of chromium will be sputtered onto the structure for improved adhesion, followed by the sputtering of the conductive gold layer, which will have a thickness of 80 nanometers. Next, a liftoff is performed using acetone to complete the pattern transfer to the metal layer. Thus, we obtain a gold metal grid with 10 micron line widths and an 80 micron pitch, fabricated on ITO. Note that the metal grid is not to scale in this illustration. Finally, we can coat the sample in photoresist, pattern, and perform a final wet etch of the ITO layer to separate the electrodes. The dimensions in the illustration to your right assume the structure will be fabricated on a 4-inch fused silica wafer. We aim to integrate 5 transparent electrodes on the wafer with widths of 1 cm and lengths of 5.5 cm. The spacing between electrodes will be 0.4 cm.
We've discussed the fabrication of the device itself, but we'll also need external circuitry to be able to use the power we generate. To take the AC output from the TNG and turn it into useful direct current, we'll need some external circuitry. Consider, for example, how a TNG could be used to charge a capacitor. The key element we need is a rectifier circuit, an arrangement of diodes that converts alternating current into direct current. Regardless of the instantaneous polarity of the alternating current from the TNG device, the arrangement of diodes within the rectifier circuit makes it so that there is always a direct current being outputted, which allows one to charge a capacitor. We can see this more clearly if we consider the 2 half cycles of the alternating currents separately. The rectifier design used in this case is a full-wave bridge rectifier, which takes advantage of 4 diodes to restrict the flow of the current. In the circuit diagrams, if we follow the current flowing from the red arrows, we can see that the current is restricted from flowing against 2 diodes, causing it to only flow into one side of the capacitor. This holds true regardless of polarity. One application for TNG devices that requires very little power is an Internet of Things integrated gravity-fed rainwater irrigation system. Rainwater falling on a roof could be collected in a storage container with TNGs placed on the roof to generate energy from the rain. This energy could then be used to open and close a valve in the water storage container, allowing the water to drain out and irrigate plants. Because the valve only needs power when opening and closing, it only requires energy intermittently, which allows the energy produced by the TNG to be built up over longer periods of time before needing to be used. Another potential application for TNGs is for self-powered electrochromic windows, also known as smart glass. These windows switch between an opaque state and a transparent state when a voltage is temporarily applied. In this case, the TNGs could be placed directly onto windows and generate power from the rain running down them. This energy could then be stored in a battery, which would then be used to switch the windows from transparent to opaque. TNGs could be integrated onto solar cells to contribute to powering large grids. This would allow for energy harvesting when solar cells are less effective, such as during a storm. By placing our TNGs on the surface of solar cells, they do not occupy any more space, effectively increasing the efficiency of the solar panels in rainy weather. As we're developing our device, it's important that we have a characterization plan to ensure that our fabrication processes have been successful. During the fabrication process, we plan to investigate and analyze the surface morphology and structure of the fabricated hydrophobic coatings and metal electrode layers. For this analysis, we plan to perform SEM on the fabricated layers. Additionally, to examine the layers after fabrication for any immediate visible defects, optical examination will be performed to analyze the layers using an optical microscope. To ensure that all desired electrical connections with the electrode layer in the device are made properly, probes in an SMU will be used to verify electrical connections. A 4-point probe measurement will also be conducted to measure the resistivity and conductivity of the electrode layer. After the device is made, a variety of characterization techniques will be needed to analyze various performance parameters. Firstly, the IV characteristics of the device will be measured in relation to the water flow rate. As the water flow rate increases, how much more current or voltage is generated. In conjunction with the water flow rate, the effect of the water charge on the performance, mainly power output, will also be evaluated. As the charge increases, the performance should increase by a certain unknown factor, since more current will be induced. The power output relation to the load resistance will also be measured, as the power output will give an important gauge as to how useful the device is. Additionally, this device power output will be tested by determining how much time it takes to charge a capacitor. Lastly, a transmittance measurement will be conducted to measure the transparency of the fabricated device using a light source and a detector. A majority of these tests will be performed using easily accessible electronic test fixtures, including SMUs, DMMs, and oscilloscopes.
After analyzing the project idea, fabrication steps, and key tests to perform, it's important to look at a roadmap for future developments in this project. Through analyzing our current progress, our key deliverables, and the resources that we have access to, we can approximate a roadmap for our team to follow until the end of April 2023, the end of our 4B term. The first item on this roadmap is to submit the proposal document by December 2021, so the end of our 3B term, which we'll use to propose our final project idea, outline the target applications, and the target performance parameters of our device. Starting January of 2022, we'll be on an 8-month co-op term. So during this co-op term for winter 2022, we aim to design and verify our device architecture with our supervisor based on the key performance parameters needed for our target applications. This includes designing the electrode and the hydrophobic surface layers and other involved device components. In the summer of 2022, we plan to design the fabrication processes we'll need to perform the fabrication of the device that we've designed. We aim to customize the fabrication processes to fulfill our device performance that we want to achieve while staying within the resource constraints. In September of 2022, in our 4A term, we'll begin to acquire the required materials and tools needed for fabrication. In October of 2022, we aim to create samples of our hydrophobic surface and electrodes while modifying the fabrication processes as needed. We'll characterize these layers and analyze whether or not we're achieving the target characteristics for those key layers. After modifying these layers and the fabrication processes as needed, we'll fabricate 1 to 2 devices in December of 2022 to test the device's power generation and the overall performance. Once we've fabricated our devices, we aim to complete the characterization of the devices in January of 2023 in our 4B term. Completing this characterization will allow us to conduct performance analysis to determine whether or not the goals we set for our device were reached. Based on this characterization, we'll reevaluate our designs as needed and refabricate devices if necessary. Lastly, near the end of our 4B term, in March of 2023, we'll showcase the performance of our final device in a practical application and demonstrate its capabilities. Additionally, we'll determine areas of future work and emphasis to pursue for future iterations of the project. For this project, along with the roadmap, we've planned out the budget as well that we'll need for the next year and a bit. The budget has been allocated towards 3 main components of the project: the fabrication of the device, the characterization of the device, and general materials costs for any tools or materials needed during the fabrication and characterization process. During the fabrication specifically, we plan to use the facilities as a part of the Quantum Nano Fabrication and Characterization Facility, or the QNFCF. The first main component within the fabrication is fabricating the electrodes for the device. Specifically, these electrodes will be in the form of the gold metal grids with an approximately 10 micron line width and a pitch of around 80 microns. The needed fabrication process for these electrodes has been previously outlined in the fabrication process slides, but we'll take a look at the tools and steps needed to perform this fabrication. Now, these tools are shown in this table, and it should be noted that the quantities, the time it'll take basically, and the cost all correspond to fabricating the electrodes 2 to 3 times. Now, this isn't the case that electrodes need to be fabricated more than once to either fabricate multiple devices or redo the fabrication with an adjusted process after the initial process is tested once or twice. Initially, in the fabrication of the electrodes, the UV semi-auto spin bake, or the Brewer UV spin bake, the front-back UV aligner, or the Heidelberg MLA, and the UV develop process using the wet bench, all of those will be used to deposit the photoresist onto the substrate and perform the baking or developing process. Once that's done, we would use the deposition twin chamber sputter, AJA sputter, to sputter gold onto the photoresist, and then the wet bench's solvent 2 would be used to wash away the photoresist, effectively completing the liftoff process and leaving the metal grid pattern. In total, given that we estimate this process would need to be performed around 2 to 3 times in case of any mistakes or changes to the process, this would cost us around $560, and these prices are outlined here, according to what's listed on the QNFCF website. The second main component of the fabrication would be fabricating the microstructures on PDMS for the hydrophobic surface of the device, given that this option is chosen over the nanowires, as the budget for the nanowires is still being worked out as well. So this would also be done using the QNFCF facilities, and as discussed in the fabrication process, we would first start off with the silicon substrate. Then, using the E-beam evaporator, we would deposit a 2-micron silicon dioxide layer. Along with performing RCA cleaning, we would also pattern the silicon dioxide layer on the substrate using conventional typical lithography, which would be done again, as outlined previously, using the UV Brewer spin bake, Heidelberg MLA, and UV develop steps. Then, using the Oxford Silicon RIE tool, a 2.5 micron deep RIE etch of the silicon can be performed using the Bosch process to develop the microstructure pattern. And then the wet benches, or solvent 2, would be used to wash off the photoresist. After that, the next steps would be the pouring and curing of the PDMS into the silicon mold to obtain the pattern structure on the PDMS to transfer it on, but that would be performed outside of the QNFCF, and so those costs have not been shown here as they're expected to be minimal. Again, we're assuming that this process would need to be done multiple times to allow for the fabrication of multiple devices, as well as to allow for redoing the fabrication in case we need to change certain steps. And with this assumption, the total cost for this process is estimated to be approximately $610. After the fabrication, the main areas of focus in terms of the budget include the characterization of the device and any general materials costs for any tools or materials needed during the fab and characterization process, as well as any contingencies which need to be considered. For the characterization, the main costs would come from performing SEM in the QNFCF. As mentioned in the characterization plan previously, SEM would need to be performed to analyze the surface morphology and structure of the hydrophobic coating and the metal electrodes. This would cost approximately $90, assuming that we need to perform SEM multiple times for a total duration of, let's say, 2 hours during the next few terms. The other characterization tests, such as IV versus the flow rate, can be performed using equipment that's easily accessible in the nano labs, such as an SMU, DMM, or oscilloscope. Therefore, the cost of those tests has not been included as they would be negligible. In terms of acquiring materials, the fused silica substrates and the ITO-coated PET films would be needed for the fabrication of the electrodes, and these would be acquired from MSC Supplies and Sigma Aldrich, respectively. 2 silicon wafers would also be bought from QNFCF for the fabrication of the hydrophobic surface using PDMS. Lastly, the miscellaneous costs include the training costs for any training which our team doesn't already have, and in this case, that's just the training to use the ICP RIE. Additionally, the contingency cost, in case any processes need to be repeated or in case any more materials need to be bought, is accounted as approximately $195, which is 13% of the total price. Altogether, this comes out to another $526. In summary, combining all the costs, the budget for this project is estimated to be $1,696. As we move forward with the project, we aim to coordinate with our supervisor to further refine our fabrication processes, device architecture, and plan for the upcoming year. Thank you.